Welcome to the Bonfiglioli webinar on permanent magnet motors for wind systems. I'm Massimo Barcaro from Research and Development Department. The permanent magnet synchronous motors are the reference technology in several industrial sectors, thanks to their superior performances. According to the Bonfiglioli experience, wind system designer may take the advantage of adopting this motor technology to improve and redesign both pitch and yaw systems. The use of permanent magnet motors can be one design step, useful to satisfy the common market requirements in terms of system reliability, gear motor compactness, overall system efficiency, profitability, and low maintenance. Thanks to a long time experience as wind customer supplier, as well as an electric motor manufacturer, also for industrial and automation application, Bonfiglioli is able to design custom permanent magnet synchronous AC motors capable to satisfy the customer requirements. Our motors are based on the interior permanent magnet technology that assume manufacturing reliability, flexible and robust design in terms of mechanical and pneumatization protocol. We are capable to provide solution up to frame ISC 200. Our customized solution can be totally enclosed or fan ventilated, and with mechanical execution according to the customer specifications. In the same way, we are able to propose a proper fail-safe electromechanical brake and an absolute position feedback to comply with the system requirements. The permanent magnet motors have well-known advantages if compared to classical induction motor. They can be differently exploited by designers according to the design optimization objectives. In particular, these motors are characterized by a high torque density that can be used to redesign the system with a smaller motor size or to improve the system performance, maintaining the present solution in terms of motor size and dimension. In the same manner, a high torque density may mean also a high torque to current ratio that is helpful to maximize the available current of the drive. Also in this case, the designer can assure an high overload torque or to achieve the same overload requirement with a more cost-effective drive. Typically, these motors have also a low rotor inertia that can be useful to increase the system dynamics with beneficial effects in terms of final actuator control rapidity. This motor must be supplied by a drive, and then to maximize the performances, it is usually adopted a closed-loop field-oriented control with an absolute position feedback on the motor. In such a way, it is possible to have a precise control of both speed and position, as well as a torque control starting from zero speed. The control is complete on all four quadrants, so both as a motor and as a generator. The motor can be easily controlled in the flux weakening operative area, thanks also to the selected interior permanent magnet rotor structure. The figure here reported shows an example of the torque-to-speed curves of both S1 flat duty cycle and the overload operations. A significant overload capability is available both in the constant current angle control as well as above the nominal speed, that is the flux weakening area. This is an example that refers to the totally enclosed, not ventilated motor. Finally, being always controlled by a drive, it is obvious that motor parameters can be constantly monitored by the system for maintenance purposes. Typically, the permanent magnet motors have efficiency higher than other motor types along the complete torque-to-speed range. So this characteristic can be exploited by the designer to optimize both the supply system, for example, taking the advantage of the regenerative braking, and in particular also the backup system for emergency operation. The higher efficiency in turn means lower current and therefore more time or operation with the same storage capacity. In any case, the efficiency increase is beneficial for the total system consumption. As cited before, to maximize the performance, it is usually adopted a closed-loop field-oriented control with an absolute position feedback on the motor. Therefore, it is possible to use the existing and proven solution available in the automation application in terms of on a selection of absolute position feedback. So it is possible to select a mechanically robust and reliable feedback among the market offers. As an example, the use of a bearing glass encoder reduces its risk of failure, and it is beneficial for system maintenance. On the other hand, there are in the market some digital protocols that have been designed to have a high immunity data transmission. So in this case, absolute encoders with this bidirectional cell interface, but also embedded safety function, may be part of redesigned safety redundant function in the system manager that can be used to simplify the physical architecture of the wind turbine. Finally, I said it before, the primary magnet motor can be completely controlled during dynamic operation, exploiting the regenerative braking, and thanks to the available constant torque at zero speed. Therefore, the brake management and design can be completely modified. Consider that dynamic braking may not be any more necessary during the normal operation. The motor can be perfectly controlled under braking operation down to zero speed, and then only at that time an holding brake may be required. This management change of the brake may be very interesting and beneficial for the system reliability and maintenance intervals, since the brake wearing is theoretically eliminated. Thank you very much for the attention.